structure. The third case was oblique instance on periodic structure. For the three cases, we discussed how to simulate these scattering events. So for all these three cases, you could use a plane wave instance and some boundary conditions. So for normal instance, you can use just periodic boundary condition or PML. And for oblique instance, you had to use a block boundary condition. But we didn't discuss the last case, the oblique instance on isolated structure. And that is the most difficult part, and we'll discuss how to do that today. So the method is called total field scattered field. Method. The basic idea is let's say we have some air and substrate. And we have a oblique instance. On this interface, and then we get some reflection and transmission. Then you'll see the pattern of the plane waves, instant and reflected and transmitted, right? And you want to capture that wave pattern within some virtual box. And then inside this virtual box, the pattern will look like so. This is instant wave, and you also have reflected wave, and then you'll have transmitted wave. So those are wave fronts. So this is the wave pattern only within this virtual box. And the basic idea of total field scatter wave method is to reproduce this wave only within the box. So we'll call this as a reference wave. So generate reference wave. Urep and hrep only within region 1. So this is region 1. And the outside is region 2. So how do you do that? So actually,
what do you mean by reference wave here?
just the wave pattern inside this region.
Oh, okay.
Yeah. So the wave that will be generated when there's an instance wave, and then it is reflected and transmitted. So this reference wave would exist all over the space, but you want to capture that only within the this box, virtual box. So actually, there exist current sources. JE and JM that generate reference wave. Only within region 1. So, by the way, by region 1, I mean the inside of the virtual box and also the boundary. So, if this region 1 includes boundary. So, what I mean by that statement is that so JM is actually a magnetic current source. You don't usually see in Maxwell's equations, but in simulation we often use this fictitious magnetic current source to generate waves. And what I mean by that statement is that for some JM and JE, you can generate E and H field with this pattern only within this virtual box, but not outside. Okay. So let's drive JM, JE. So strictly in region 1, you have this equation satisfied. Right? Because this wave pattern satisfies Maxwell's equation, right? And this is just Maxwell's equation. So that reference wave should satisfy these Maxwell's equations within that virtual box. So this means JM and JE are 0. Inside region 1. And also, strictly in region 2, E and H field are 0. So JM and JE is also 0 in region 2. Any questions on this until FML. So when you have a solution of Maxwell's equations, that should satisfy Maxwell's equations, right? So I'm just saying that. And now we'll look into boundary of the box, virtual box. So at the interface between region 1 and 2. So this is region 1, region 2. So we have East grid, and these are EX, UI, and HG components. And I said that region 1 includes this boundary, right? So for this curl loop, the E fields are all E field of the reference base. And H field here is also the H field of the reference base. So in this cell, you satisfy Maxwell's equations. Exactly this one, right? And in this cell, E field is 0, and H field is also 0. So you satisfy this equation. So I'll call probably this equation 1. And this equation 2. So in this cell, you satisfy equation 1, and in this cell, you satisfy equation 2. But in this cell, so let's denominate this point as point A and this point B. At point A, your curl is not 0. At point A, your curl is not 0 because in the this is important. So EY here is the E field of the reference weight, right? But at all three sides, E field is 0. So the curl, if you calculate the curl loop here, then it is non-zero. So the curl is non-zero at point A. And the H field at the point A is still 0, right? Because it is in region 2. Therefore, your JM, which is minus mu0 dth minus curl E, is non-zero. So to summarize, JM is non-zero at point A. So to generate that reference wave, you have to have magnetic current source at point A. At point B, we actually need to think about this dashed E cell. point B, your H field is still on the boundary of the region 1. So your H field is H field of the reference plane at point B. But your curl of E is not curl of E field of the reference plane, because I'm sorry, yeah, I got messed up. So here you have EG defined, right? The E coming out. So you have EX, EY, EX here, EY here, EX here, and EY here, and EG is defined on the edge coming out, right? So at point B, your E field is still E field of the reference wave, but the H field is these three H field here and here and here are the H field of the reference wave, but H field here is 0. So curl of H is not curl of reference plane. Okay, so that means JE, which is curl of H plus epsilon dt E is non-zero. So with such defined JM, JE, E field within region 1 is E field of the reference wave, and H field in region 1 is also H field of the reference wave, and E field in region 2 is 0, and H field in region 2 is 0. So reference wave exists. So if you have such Jm and Jne around the boundary of the region 1 box, then a reference wave is generated strictly inside region 1 and boundary. So you may think that you may have wondered how we generate such a strange wave only within the box. But these arguments shows that there's some current sources that generate such a reference wave only within the box. That is the important part of appropriate scalar field wave. Now add a scatter. gets scattered, reference wave gets scattered. Okay, so in region 1, the field is reference wave. Scattered wave. And in region 2, is so I'll show the movies soon, but so you had this kind of setup, and you had a reference wave generated inside the box, right? And let's say you had you put some scatter here. Then on top of the reference wave, the current induced current on scatter wave generate scatter wave, right? So within the box, you have the some of the reference wave scatter wave, but the scatter wave propagates outside of the box. So outside the this region 1, you have scatter wave. So here inside the region 1, you have reference wave plus scattered wave, and outside you have scatter wave. So region 1 is called total field region. And region 2 is called scatter field. Okay. I'll show you the total field scatter field in action. So first one is this. So this is just vacuum. There's no substrate. So you generate just plane wave only within some partial box, the total field region. I'll just play this again. So you can see that some current source actually can generate this wave strictly inside the region 1 boundary. And if you put a scatter, in the same way, interacts with scatter, and generate the scatter wave. So I'll stop movie here. So you can see that there's some boundary here, right? So in this boundary, you have the sum of this scatter wave and instant wave. So inside this boundary, you have the total field. But outside the boundary, you only have the scatter wave. And I'll show the case with scatter substrate. Sorry, I've overwritten some movies, so I cannot show the case where there's substrate but no scatter. I'll show you the case where there's substrate and scatter. So you can still see that there's a reference wave propagating inside this region. But outside of this total field box, you have only scatter wave. So yes, and then later you see the boundary here. So within this above this boundary, you have the sum of the transmitted wave of the reference wave and the scatter wave. But outside this box, below this boundary, you only have the transmitted part of the reference wave. I mean, the transmitted part of the scatter wave. So, are there any questions?
So does this analysis, at least with a lot of these commercial software packages, only hold for flat substrates?
I'll discuss that
Okay.
soon. Yeah, actually, let me show the movie first.
Like the key seems to be just solving for JE and JM, irrespective
Right,
of the
right.
substrate. So the substrate could potentially be some
Right.
strange shape, but then the substrate also, in a sense, becomes the scatter.
Right.
Or
So,
a scatter.
this is the case where I wanted to treat this bump as a substrate, part of the substrate, and later on I wanted to put